ways to share with all again. Okay. Now, as shown on this slide here, this is the first slide that I will use for this lecture on EAS663, which is on stability of structure part. Okay. Now, in the first part, week number 1 until week number 6, it was right until last week. I think you have been taught these basic things and also some of the important things about solving problems related to dynamics of structures. So by now you should be familiar about equation of motions for single degrees of freedom and also for multiple degrees of freedom. How do you get them? And how do you model them as single degrees of freedom? And how do you model them as multiple degrees of freedom? And how do you actually get this equation of motions, which is a second order ordinary differential equations? So whether it is free vibrations, where there is no forcing function on the right-hand side of this equation, or there is a forcing function, which is a force vibration, where you have a forcing function on the right-hand side here, which is not zero. And you learn also how actually you should solve these equations. It eventually, to determine in the dynamics of structures, we want to solve for frequency, or what is the period of vibrations, the frequency or the corresponding period of vibrations. Once you know frequency, you can get the period. And if the structure is going to vibrate, what is the mode shape? What is the first mode shape, second mode shape, and the third mode shape? And how do you get it by solving the equation of motion? And if the structure is set into motions with some initial conditions, so what will be the time history? So that is how you, for example, displacement or accelerations or velocity or internal forces will change with time. So this is the time history of response. So this is what dynamics of structures is about, and you have learned this. So the second part that I'm going to cover, as appeared in the title here, class, is stability of structures. The same thing later we will see. The same thing we have to get what is the equations. Yeah, what is the equations governing stability of structures? So governing equations. So governing equation means the equations that we need to use to solve problems of stability of structures. And once we know how to get these governing equations and what are the process that we have to go through, what are the assumptions that we have to make, and what are the methods that we have to solve it, then we want to get from the governing equations here the buckling load. The buckling load, or sometimes it is mixed, used together with critical load. Then another one is the buckling mode. Buckling mode. So that is the thing that we want to determine. Okay. Now, later, I will spend some time first explain to you what is the meaning of critical load. So you need to get understanding clearly what is the meaning of critical load. So critical load, as written on this slide, can be understood as first limit of load. If you exceed that load, beyond which then loss of stability will occur. Okay, so this is critical load. So if you everything below that load, then the structures or the shape, the deformed shape is still stable. If anything beyond that load, more than that load, then that particular shape is no longer stable. Okay. So that is the first thing that I would like to make it clear to you all, the concept of critical load, or the concept of stability. Now, please make sure, Go, I think your mic is on. Can you off your mic, Go?
Oh,
Who you mean?
gosh.
Who you mean? Good morning. Can you please off your mic? Thank you. Please off your mic. Thank you. Now, class, I show you here the example of 2 bar, okay? They are exactly identical. You consider this as a bar. On the left-hand side, I call it case 1. On the right-hand side, I'll call it case 2. And they are exactly identical in the sense that they are the same cross-sectional area, same material, same length. And they are all subjected to axial load at the end here. But the only difference between them is, as you can see from the directions of the load applied here, the one on the left-hand side, case 1, is the bar is being pulled, and the one on the right-hand side here, case 2 here, the bar is being pushed, which means this bar is subjected to tensile force, this bar is subjected to compressive force. As a result, you develop tensile stress, the bar become longer. On the case 2, the bar, you develop compressive stress, the bar become shorter. Okay? Now, I would like you to now imagine, I think, if we do an experiment using identical bar like this, case 1 and case 2, one we pull and one we push. Okay. So, and we want to know what will be the possible response of this bar, case 1 and case 2, as we increase the load. As we increase the load, what will happen? Okay. Now, on the case 1 side, which is the bar in tension. Now we are very familiar if you are pulling a bar, for example, a steel bar, pulling a bar in the machine, we pull it, so the bar will get longer, and finally the bar will fail when the capacity of the material is exceeded. So the ultimate tensile strength, ultimate strength of the strength of the bar has been exceeded, which means the bar will finally fail, and then it will fail into 2 pieces. Okay. So that is material failure. Okay. On the other hand, for case 2 here, if we continue pushing this, put this in an experiment, continue pushing that, so there is a possibility that this bar might fail because of material capacity failure, which is you keep on pushing until the compressive strength of this bar has been exceeded. Then you have a crushing. Somewhere you have a crushing of the bar somewhere, and because the material strength has been exceeded, which is in the sense similar to here. So you have material failure. Okay. Now, if you are familiar with, if you try to do the same experiments with a ruler, okay, with a ruler, and you try to push the ruler. So later class in the class on Thursday, I will try to demonstrate to you some of these things. Online is difficult for me to demonstrate. So I would like you to imagine if you have a ruler, okay, you push the ruler. If you push the ruler, let's say the common plastic ruler, you keep on pushing it, then most likely you have already experienced that. Suddenly, when you push the ruler is going to bend sideways. The ruler will not be crushed. The ruler will not be crushed, but the ruler suddenly will bend sideways. Okay? Which means you keep on pressing, suddenly the ruler will bend like this. Instead of having material failure. Instead of having material failure crushing here, the ruler will bend. Okay? So this is one of the fundamental difference that we will see in the response of case 1 bar and case 2 bar. So in the case of case 2 bar here, we have this particular failure mode, which is different from the case in tension. So in case 2, the member in case 2 might fail by sudden bending. instead of material failure. Okay, instead of having fail here, material crushing, then it might fail because with sudden bending of this member here. So this is a classical example that we can relate to for the case of bar in compression, and this sudden bending, we suddenly call it the column problem. Okay? Column is a member which is normally carry axial load, and column has this problem that we need to specifically pay attention to, which it will fail before the material fails by sudden bending. It is initially straight. If you keep on increasing the load P, and at certain level, you will see the straight is no longer straight, it will suddenly bend. Okay. So this is the phenomena that we are concentrating on. Okay. And the next slide, I'm going to introduce to you now the concept of stability. Okay. Now, class, stability here, you should understand this as a word that we use to describe state of equilibrium. We use it to describe a state of equilibrium. So what is the meaning of state of equilibrium? We'll come to that. Now, equilibrium, we know equilibrium. This is a fundamental concept that every one of you should know. This is a positions. There are positions where internal force equal to external force. This is equilibrium. This is equilibrium. And stability is a words that we use to describe the state of that equilibrium. So the state of that equilibrium is represented by these three diagrams here. So the first one, the state of that equilibrium is stable. The second one, the state of that equilibrium is neutral. And the third one here on the right-hand side here, the state of that equilibrium is unstable. So stability class, please remember it is a word that we use, a concept that we use to explain what is the state of that equilibrium. Is that equilibrium a stable one? Is that equilibrium an unstable one? And is that equilibrium a neutral one? Okay. And in the next few slides, I'm going to explain to you how do we differentiate and how do we know that equilibrium is stable, unstable, or neutral. So in order to be able to explain what is the state, which means what is the stability of that state or of that equilibrium state, we need to closely relate, we need to closely observe what happened to that equilibrium if it is disturbed. If it is disturbed. So the important words here, which is closely associated with the understanding of concept is stability, is disturbance. Okay, what happened to that equilibrium if equilibrium positions, if it is disturbed? You have to observe after you disturb that equilibrium positions, will it stay in the same positions? Will it go back to the same positions, or it will not go back to the same positions? So class, remember, stability is closely associated with what happened to the equilibrium positions after it is disturbed. Will that equilibrium position be maintained? Which means it will go back to that equilibrium positions, or it will not go back to that equilibrium position. So we have to disturb it to know the state of that equilibrium, whether it's stable or unstable or neutral. So next, I'm going to explain to you using these three diagrams here. Okay, how do we classify this as stable? How do we classify this as unstable, and why we classify this as neutral? Now here we show you a ball here. which is located in the surface like this. The top of the diagram first. Now, if you imagine, okay, if you imagine that this ball, which is in this equilibrium positions here, the lowest point here, and you disturb the ball, you disturb it. You can disturb it either here or there, you disturb it. Okay. Then what will happen is the ball will swing here and there. The ball will move up here. If you disturb here, then you take away the disturbance. You disturb here, you take away the disturbance, then the ball will go here, and then come back here again, go there again until finally it will go back to that state again after disturbance is removed. So under this kind of situation as shown on this slide here, the top diagram here, so if the ball is disturbed slightly from its original positions of equilibrium, so if disturb it slightly, then it will return to the positions which is in this original positions here, subsequent to the removal of the disturbance. You disturb it, and if you remove the disturbance, so eventually it will goes back to that equilibrium positions. So for this case, this is called stable equilibrium. Now, we can relate this to the case of a simple case like a column here, a cantilever column, fixed here, and that is subjected to a axial load P here. Now we know that if you apply the load P here, then this equilibrium, this straight one is an equilibrium position because you can have this P, then you have an internal force here, F. So in this straight positions, the column is in equilibrium under the action of load P. Now at a certain level of load P, when the column is applied at a certain level of load P, and then you disturb this column, you disturb it. Okay? You disturb it, let's say the top part, you disturb it. Where the load P is still being applied there, you disturb it, and you disturb it at the top part there. And if after you remove the disturbance, that column will eventually goes back to the straight positions, the original straight positions, then that column under that load P is in stable equilibrium. So if we explain this, if the straight positions of the column, which is in equilibrium under the load P is disturbed, it will return to the straight position subsequent to the removal of the disturbance. So in this case, this column, which is straight in the straight configurations under the action of load P at certain level, is stable. So next, if we move to unstable, just now we look at stable. Now, if we move to the case of this diagram here, the top part first, just now we have a diagram where it is the ball is located in here. Now is inverted. Ball is located on the surface which is inverted from the previous one in this situation like this. Now in this case, you can easily imagine if the ball is disturbed slightly from its original position of equilibrium, even if you disturb it slightly, you disturb it slightly to here, then it will not return to the original positions. After you remove the disturbance, instead, it will continue to move further away from the original position until you find another position. So for this case, where if you disturb the equilibrium positions and subsequent to the removal of the disturbance, the equilibrium position, it will not go back to that equilibrium positions. Instead, it will move further away. This equilibrium is called unstable. Again, if you use the example of a column subjected to axial force, and it is in equilibrium in the straight configuration here, and if you keep on increasing the load P, and then at certain level, a certain magnitude of load P, where the straight one is still in equilibrium, if you disturb it, If you disturb it, then if the column in the straight configurations under that load P will not return, it will not return to the original configuration. It will not return to the straight one. If you disturb it, it will not return to the straight one. Instead, it will go further away from the straight one and maybe go to this bend one here. Then this is called unstable equilibrium. The straight one is called unstable equilibrium because it cannot be maintained. It cannot be maintained after you remove the disturbance, which is the case for the previous one when we talk about stable equilibrium. So if you look at the explanation here, if the straight position of the column, which is in equilibrium under the load P, is disturbed, if you again disturb it, it will not return to the straight positions subsequent to the removal of the disturbance. Instead move to a bend configuration, which means the straight one is not stable anymore. It cannot maintain that equilibrium positions. So now if we extend this to the third state, which is in between stable and unstable, which is neutral equilibrium. So we have cover case like this. We have cover case like this, where there's a ball located here, there's a ball located here. Then now we look at this case where it is flat. So in this case, if the ball is disturbed slightly from its original positions of equilibrium, if it is here, then we disturb it slightly to here. Then what will happen is that after you remove the disturbance, it will neither return to the original positions, which is the case for stable, and it will not also, nor continues to move further away, which is the case for unstable. Instead, it remains at the position where the small disturbance have moved it. So if you disturb it here, it will not return, but it will not move further away, but it will stay wherever the disturbance has moved it after the removal of the disturbance. So for this case, this equilibrium positions is called neutral equilibrium. So again, if we look at this case of a straight column under the actions of this compressive load P, which is in equilibrium, and at certain level of load P, if you disturb these straight positions of the column, then this for neutral equilibrium, when you disturb it, after you remove the disturbance, it will not go back to the original straight positions, and also it will not move further away. Not like the case where it is unstable, it will move to the bend position, it will not move further away, but instead it will remain at the slightly bend. Wherever you disturb it slightly, it will remain at the slightly bend positions where the disturbance has moved it. So this equilibrium positions is called neutral equilibrium. So now if we combine all these three together, we use the case of a cantilever column subjected to axial compression at the top here. And I show here on the left-hand side, this P is less than certain critical value. On the right-hand side, this P is greater than certain critical value, which is called P critical. And at the center here, we have the situation where P is exactly equal to P critical. Okay. Then, for this one on the left-hand side, when you disturb this, when the load is less than P critical, this column will eventually return to the straight positions. And for this case, when the P is more than certain critical value, if you disturb the straight positions when P is greater than P critical, then after you remove the disturbance, it will not go back to the straight one. Instead, it will go to the bend one here. And the center one here, when P applied here on these straight configurations is exactly equal to P critical, then when you disturb it slightly, you remove the disturbance, it will not go back to the original straight one. And also it will not move further away to this bend configuration like what happened here, but it will stay at the slightly bend configuration. So if we come back to this case, when P is less than P critical, the straight configurations is stable. As long as P less than P critical, you disturb it, finally it will goes back to this state here. Okay. So when P is less than P critical class, only the straight position is possible. Because if you disturb it, finally it will go back to this equilibrium position, which is a straight one. So only the straight position is possible. On the right-hand side here, we go to this right-hand side here first. Now, if P applied here on these straight configurations of the column is greater than certain critical value, then when you disturb it, it will not return to this, but it will go to this bend configurations. So for this case, when P greater than P critical, the straight one is not stable anymore. And the only one which is possible is the bend position configuration is possible. So when P greater than P critical, we cannot have this straight configuration as the equilibrium positions. The only one possible is the bend one. Now we come to the transitions here. When you P increase until approaching P critical, and then right at the P is equal to P critical value, what happened is both the straight and the slightly bent position is possible. Both is possible. The initial straight one and the slightly bent one are both possible. Exactly when P is equal to P critical. Here, only the straight one is possible when P less than P critical. Here, only the bend one is possible when P greater than P critical. But at this neutral equilibrium, both straight one and the slightly bent positions is possible. So this is a state that we call state of transition from stable to unstable equilibrium or neutral equilibrium. And the concept of neutral equilibrium, where the straight one and the slightly bent one is possible, is later being used as one of the method, is being used in one of the method to determine what is the P critical. So from this slide here, you can see P critical is the limit. It gives you the limit below which the straight one is possible, is stable. After that, the straight one is not possible anymore. So this P critical is an important value that we have to determine. And one of the methods that we are going to look at first is using the concept of neutral equilibrium to determine this P critical. So this is a summarize of what I have mentioned just now. So neutral equilibrium, which is a state of transition from stable to unstable, is the positions where is the state where both the straight one and the slightly bent one, after you disturb it, is possible. So these two possible equilibrium positions at the state of neutral equilibrium. So if you look at the explanation here, the load at which the straight configuration of the column ceases to be stable is the load at which neutral equilibrium is possible. And this load is called the critical load. So the load corresponding to the neutral state of equilibrium is called the critical load. So to determine, using this concept of neutral equilibrium, to determine the critical load, To determine the critical load, we need to find the load, in this case the actual load, under which the member can be in equilibrium in both the straight and in the slightly bent configurations. Okay. And the method that makes use of this concept of neutral equilibrium to determine P critical is called method of neutral equilibrium. The method of neutral equilibrium makes use of the concept of neutral equilibrium to find P critical. Neutral equilibrium means the equilibrium positions where both the straight one and the slightly bent one are possible. So two equilibrium positions are possible at neutral equilibrium. So this is the first part that